All right, guys, we're going to do a crash course on Chapter 4, Study Guide. So the first thing that we talked about was reading and interpreting graphs. So looking at this graph here, I need to notice a couple of things. First of all, this is about ice cream cone sales. And along the bottom, we have days of the week. And then along the side here, we have the number of ice cream cones sold. So I could say something like from Tuesday to Saturday, sales decreased. So ice cream cone sales decreased because that line started up at 70 and ended down at 60. We could also say something like from Saturday to Thursday. So from Saturday to Thursday, ice cream cone sales went up, increased. Now I would say they increased quite a lot, but you could just say increased because the thing is, this increase compared to that one is a little less, but I mean still an increase, okay? And then jumping ahead just a little bit, so we have like decrease, increase, decrease, increase, but this line right here is interesting. So from Friday to Wednesday, here to here, ice cream cone sales stayed the same. Or another word for stayed the same could be remained constant. Okay, and then we have a big old decrease again here. Okay, so just some ways that we can read and interpret a graph. That was kind of the first thing we did. Second thing we talked about is it a function or not? And so I can tell that something is a function different ways depending on what I'm looking at. So with the first one, this graph right here, or this table right here rather, I can tell that that one is a function because all of the x values are unique. So x values unique, that means it's a function. For the second table here, going right across, I look at the x values, and again, they're all unique, so also a function. That third one though, if we take a look very closely at our x values, I have a repeated x value. So there's a 1 here and a 1 there. And when I go to check their y values, they are different. So this right here tells me that this will not be a function. So x values repeat, not a function. Okay, so it's all about that x. So another way to look at this is if we were to look at the graphs. So if I take a look at this graph right here, we do what's called the vertical line test, which basically just means if I put a vertical line through any part of the graph, as long as it only touches one spot at a time, it's all good. So this graph is only made up of points. And if I draw a vertical line right here, touches once, so it's fine. Touches once, so it's fine. Touches once, so it's fine. So for 4, that is a function. It passes the vertical line test. For number 5, looking at that graph though, this vertical line is fine. So is that one. But the moment I draw a vertical line right here, it touches 2 spots, so it fails. Not a function. So not, and it fails the vertical line test. Now another way to think about it is looking at a mapping diagram. So the 6th one here is a mapping diagram. And again, we're just checking our x's. Another word for x is domain. And as long as my domain values are not repeated, so I'll know that they're repeated in a mapping diagram if there are 2 arrows coming out, because that's showing me that this number is paired up with that one and this one, and that's not okay. Like 1 was paired up with 5 and 0, not okay. But there's only 1 arrow coming out of each, so that's a function. If we take a look at number 7 right here, when you just have ordered pairs, you could do something like make a mapping diagram, but we're really just concerned with the x values. And if I look at each one, they're unique, so it's a function. This next one here, this list of points, again, if I look at my x values, I got -1, 3, 3. So an x value repeated, and this one's paired up with a 2, and that one's paired up with a 0. So right now I know not a function. And it's not a function because, again, 3 is paired up with 2 different numbers, and that's not okay. And then this last one here, we got 1, 2, 3. All those are different, so that is a function. They're all unique. Okay. Next, we talked about function notation next, but I'm going to do domain and range. So with domain and range, domain is just the fancy word for what are the x values, and range is just the fancy word for what are the y values. So if I'm looking at something like this, it's super easy to just list all the domain values because I can just see them. There's a 1, a 2, and a 3. As far as the range value goes, those are all the y values. And in this mapping diagram, there's a -3 and an 8, and that's it. Now things get trickier when I look at a graph that is continuous or like a filled in line, something like these examples here. And so if that's the case, that's when I have to start using my less than or equal to or greater than or equal to stuff. So for this graph here, when I'm looking at domain, because it's a continuous graph, I cannot list all the x values here. Sure, I can see that there's an x value at 0, and 1, and 2, and 3, and 4, and 5. But there's a whole bunch of values in between that I can't list. So because of that, we use those inequalities. And for domain, we look from left to right. And this graph is as far left as that and as far right as that. So the smallest that it gets is 0. All the x values are in between that, and it gets as big as 5. And so when we have this in between stuff, we use our less thans. And in this case, it would be equal to because they're filled in dots. Now, when we're talking about range, range is up and down, or y. And this graph gets as far down as that and as high up as that. So the smallest that y ever gets is -2. And then all the y values are in between that and the biggest, which was 3. So again, because it's just like that last one, we're using those less than or equal to's. And it's equal to because those are filled in dots. Now it gets even trickier when I have arrows. So this had in-betweens because it had a beginning and an end. With arrows, I might not have a beginning or I might not have an end because arrows imply forever. So if I have arrows, I want to think about which way they are pointing. Now when it comes to domain, we're thinking about left and right. And this graph is pointing left. And this part of the arrow is pointing right. For range, we're thinking up and down. And this arrow is pointing down. And so is that one. So when I think about domain, this graph is pointing left forever and right forever. So eventually, it'll get to all those x values. So all real numbers. When I think about range, range is up and down, but this graph is only going down. So that must mean that the y values are getting smaller, because down, so smaller than some top value. So like how high did this graph get? Well, this graph got as high as -3 right there. So all the y values are less than or equal to -3. Okay, so you might just have one inequality if it continues in one direction forever. This one had two inequalities because it had a beginning and an end. It didn't have arrows. Now this graph here has arrows on both ends, just like that one. So over here, if I'm thinking about left and right, this is pointing left. This is pointing right. This arrow over here is pointing down. This arrow over here is going up. So if I think about domain, we're going left forever, right forever. So that's all. And if I'm thinking about range, range is up and down, and this graph is going down forever and up forever. So that's all. Okay, on to the next. When we talked about function notation, that's where I maybe gave you a graph, but oftentimes I gave you a function. So like f of x equals -x squared plus 3x minus 3, or g of x equals half x plus 5. And I asked you to plug some things in. So for example, if I said, let's do f of -1. This is telling you need to pick the f function, and this is showing you what you should input or put in for x. So in place of x, with parentheses, I'll put a -1. And then we just simplify until we get our final answer. We never do anything on the left-hand side. We just simplify over here by following good order of operations. So I would square -1. So -1 times -1 is +1, but there's a negative in front of it. So overall, we're -1. Right here, when I multiply 3 times -1, that's going to be -3, and then -3 more. And so when I combine all these up, -1 minus 3 is -4, and then -3 more is -7. And so all I'm looking for is my output. So -7 would be my final answer. Another example of this could be g of 4. So this is showing me I need to pick the g function. And then this is showing me what I should input into it in place of x. So in place of x, I'll put 4. And then I'm going to follow good order of operations to find my output value. So half of 4 is 2, plus 5 is 7. Ooh, I didn't even mean to do that. Look at how fun. Okay, there you go. The last thing that we did was decide if stuff was linear or nonlinear. Okay, so if I'm looking at a table, I can tell if something is linear if it increases or decreases by the same amount every time. So if I look at the y values, this is going up 2, up 2, up 2. So that would be linear. I can tell from an equation if it's linear or not. If x does not have an exponent, if it's not in the denominator, or anything like that. So this x does not have an exponent, and it is not in the denominator, so this is linear. I can tell from a graph if it's like a straight line, no curvy, swervy stuff. So this is nonlinear, because that's a curve. This one, again, looking at the equation, has an exponent, so nonlinear. Looking at the table here, I can see that this goes up 1, up 1, up 1. But the x values aren't moving, so that's weird. Like the x values go up 6, up 10, up 12, so nonlinear. because this is not moving at the same speed every time. This equation here, nonlinear, because of that exponent to the second power. This graph, though, that's linear because that's just a straight line. That one is curvy, though, so nonlinear. And then this table here, so the y values are all going up by 1, and the x values are all going up by 2. So because they're both moving at a steady pace, like adding the same amount every time, that is linear. Now, we also did stuff with patterns to determine if things were linear or not. So with this one here, I noticed that I kind of had this little baby L shape. And then when I went from this one to that one, I noticed that they put a star on either end. And then they did that again. And so if I draw this out one more time, to make the next step, that can be helpful to then make a table. So if I make a table of values, I put the step number and then number of stars. So in the first step, there are 3 stars. In the second step, there are 5 stars. Right? Yeah, okay. In the third step, there are 1, 2, 3, 4, 6, 7 stars. And in the fourth step, I had 1, 2, 3, 4, 5, 6, 7, 8, 9 stars. So thinking back to what we were just doing in the last one, I can see that these are increasing by 2 every time. So the pattern is growing by adding 2 each time. So how many in the next step? Well, the next step that I drew there are 9, but if I want to go one more, that would be 11. And so to write the equation, whatever number you're adding over and over and over again gets multiplied to x because we are linear. So it'd be 2x because we're adding 2 each time. But if I go try this out, 2 times 1 is 2, but I was supposed to have 3. So I kind of need one more. And if I try with the next one, 2 times 2 is 4, but I have 5 stars, so I kind of need one more. So since I'm needing one more, I would just put plus 1, and then it all works out. And so when I go to graph this as well, I can just plot my points. So 1, 3, 2, 5, 3, 7. And you can also see that this is making a nice straight line. So all these different ways I can tell, again, that it's linear because it makes a nice straight line graph. The table is increasing by a constant amount. And in my equation, x does not have an exponent and it's not in the denominator. Okay, so one more to try. If we take a look at this pattern here, the way I kind of see it growing, so I got these 4, but then it looks like it wraps around, and then it wraps around. And so if I create that again, I'm just going to do dots. 1, 2, 3. If I make a table where I do step and then number of diamonds or dots, in the first step I had 4. In the second, it's like a 3 by 3, so 9. In the third, 16. And in the fourth, I had 25. And so if I think about how the pattern's growing, if I try to do what I did on the last one by adding, here I have to add 5, but here I'd have to add 7. And here I'd have to add 9. So I'm not adding the same every time, which means that it's not linear. But it is sort of following a pattern of like adding odds. And so since that's the pattern, I would have to add 11 on the next one. And so that means the next step would be 36. And we don't need to worry about equations so much on this one, but it is important to know that it's nonlinear. And I can see that as well in the graph, because if I were to plot this, so like 1, 4, 2, 9, 3, 16, this would be moving very, very quickly and not be a straight line. It's going to be a curve. So I can also tell nonlinear. All right, there's your study guide. I know that was long, but that was a whole chapter.